participants, so we are missing people, but that's fine. I'm gonna make it quick lecture today, so I don't want to keep adding in the top of your head. So if for those people who didn't have enough time to study, so it will be enough for them to study more and more and more. And let me access my tablet, and then we can start moving forward. Everybody can see my screen?
Yes.
Mutability. 2300. Okay, ready? Now we're gonna talk about encoders. So the first thing that we learned before, it was called majority encoder. What is majority encoders? I'm just refreshing your knowledge. So basically, majority encoder, that, you know, if you think about it from like a circuit perspective, I have a bunch of inputs and I'm trying to select based on the regulation I already set it up, right? So for instance, if I have n inputs, I'm expecting output. Make sense? And from there, I need to set up a regulation. What is the relation between this input and outputs? Maybe majority for me, I'm looking for majority of ones. So that means, you know, I'm looking for how many inputs are holding one while the rest are zeros. And I'm making an assumption that, you know, the one holding ones, it will be considering the output is one if they are more than the one that has zeros, or the vice versa, it will be zero. Maybe, you know, you can make it in a way that, you know, the majority encoder set it for zero. So that means I'm looking for the how many one has zeros, and I'm putting an assumption that, you know, if those have zeros more than the one have one, then in this particular case, the output will be one or zero. It depends whatever I want. That makes sense?
What if your zeros and ones are equal in input?
Then, you know, that's part of your setting up, right? So you can come and say that, you know, I'm really tied to my constraint, say that, you know, if they are actually equal to each other, then it will be zero, because, you know, my target is the one greater than the others, right?
Correct.
Or you can actually set it up a new regulation, right? You can come and say that, you know, when I see them equal to each other, then my output will be high impedance.
So you
what does it mean?
Want, right?
Yeah, so what does it mean, high impedance, right? So if you guys remember, we said bit can be 1, can be 0, can be I don't care, can be high impedance, Z. So it can be 1, it can be 0, it can I don't care. And then, you know, Z, it means that, you know, it's floated, it's not connected to anything. That means the current in this situation equals 0. Sometimes they need this because, you know, imagine that, you know, I already have a very sensitive electronics and have been launched in a satellite. And then, you know, this satellite, you know, is facing some particles coming from one of the stars nearby. I'm not going to say sun, but anyway, then, you know, these particles will hit the chip. Then there is something actually called this soft error rate and hard error rate. What does it mean? It means that, you know, one of those particles can flip the electrons inside the chip and make it 1 instead of 0 and 0 instead of 1. So in that case, you know, the chip designer, especially for space application and even military application, they will come and say, if this such kind of situation happen, then, you know, I can make a short circuit in my circuit, and then, you know, the whole entire satellite will be fried, and then, you know, the gravity will suck it up, and then, you know, we'll be in a big trouble. So in that case, they say, if this scenario happen, I'm going to make it Z. So then, you know, you know, sections inside the chip will be turned off, and the rest of the section on the chip will be working fine. That's a very severe situation. But okay, so Z, it's something can be holded in a bit. X can be holded in a bit definitions, and 0 and 1. So you can come and say that, you know, I would like my majority encoder to have the majority of ones, but, you know, when I see that, you know, cases of they are equal to each other, make it Z. Should we make an example for this?
Sure.
So imagine that, I have here 3 input majority encoder, 3 input. And I have an output. And I set my rules. So my rule said that, I'm looking for majority of ones. But in case of equality, right? Output is declared as X. Okay, so then I will open my states here. So this table will be describing the relation between input and output. Do you agree? So how many inputs I have in this case? I have 3, right? So this 3, you can draw how many states inside the table?
8.
8 states, correct. So, I can just go and see 1, 2, 3, 4, 5, 6, 7, 8. Then, let's make a symbol for our variable names for the inputs, right? So going to be X, Y, Z, right? So I'm going to call it X, Y, Z. And let's assume the output is called P. And P is a function of X, Y, Z as a variables, right? So then I'm going to fill it up. Those are the main terms, if you guys remember, right? So now, in this particular case, it's very obvious that, 1 is not winning, right? Because all of them are zeros. Do you guys agree? So the output in this case, 0. Then, in this case, I found 1, but how many of those ones exist? It's 1 versus 2 zeros, right? So still, this is winning. Then 0 and 1 is still going to be 0. Here, 1 and 1 is going to be winning. Here we're going to be 0. Here we're going to be 1. Here we're going to be 1. Here we're going to be 1. This particular case, it didn't show me what X, because there is no way for you to have half and 1 and half, right? You agree?
Yes.
Yep.
Even I already have assumption. When this will happen, if number of inputs are even. Do you agree? So then in that case, I can just make it 4. So X, Y, Z, W. So how many states this table will be covering?
16.
16. So going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? So 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, then 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Then 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Then here 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 6, 7, 5. Right? Some of the cases here, I'm not going to go through it. I will just show you some cases, right? For instance, this case, right? There are 2 1s and there are 2 zeros. So here's equality, right? So they are equal to each other. In this case, I will put this as what? X. That makes sense?
Yes.
Then you will just do the rest of the following. And then, you can play with this X to make the best optimization for you, right? We can, you know what, let's finish it. It's not a problem. So here is 0. Here is 0. Here is still 0. What about this case? It's going to be what? Somebody can tell me.
0.
0.
0. This case is what?
X.
X. This case is what?
X.
X. This case is what?
1.
1. Oh, sorry, I don't know what this 0. Anyway, this case is what?
X.
Right? Huh. This case is 1 and this case is 1. Right? Now I can literally go and build my K-map, right? 1, 2, 1, 2, like this, right? That was X, Y, Z, W, right? So X, Y, Z, W, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, then 1, 1, and then 0, 1. Location 0, location 1, location 3, location 2, location 4, location 5, location 7, location 6, location 8, location 9, location 11, location 10, 12, 13, 15, 14, right? So let's go ahead and see what we are doing here. So, location number 3 is X, right? Location number 5 and 6 are X, right? 5 and 6 are F. Location number 7 is 1. Location number 9 and 10 are X. 9 and 10, right? 9 and 10. And location number 11 is 1. Location number 12 is X. Location number 13, 14, 15, 13, 14, 13, 14, and 15 are 1, and the rest are zeros. Everybody agrees with me? Correct?
Yep.
So now we're going to benefit from X, right? Why? This is a group, and this is a group. Correct? So I can come and say P as a function of the X, Y, Z, W is equivalent to group 1, or it was group 2, and this is group 1. So group 1 is what? It's going to be XY, right? Group 2 is what? WZ. And that's it. So can you imagine? So the majority encoder with a specific constraint, I have set it up by making the equivalency or equal of number 1 and 0 is X, will end it up to be 2 and 1 OR gate. Any question?
Nope.
Any answer? Anything? So let's see what else I would like to share with you today. So what about Bcd Adder? You guys heard about Bcd Adder? In BCD, just reminding you, right? The digit is represented by 0 to 9. You guys remember that?
Yes.
Yes. And if we are going above 9, we have to return it back to 9, right? Or 0 to 9. And we define 0 to 9 using how many bits? 4 bits, right? But those 4 bits, capacity-wise, is covering 0 to 15. Do you guys agree?
Yes.
Then we came into the conclusion from 10 to 15s are not desired, right? And how many elements of this pile we are covering? 10, 11, 12, 13, 14, 15, 6, right? So we came into the conclusion saying that, everything above 9, it has to be at to 6, then it will trim back to 0 to 9. Do you guys agree?
Yes.
So everybody know that, or some of you know that. So, if it's clear, write clear in the chat. So at least I can see what's going on. Just one person said clear. Oh my gosh. Oh, Diamond clear. Okay. catch him, by the end of the lecture, we will sell the diamond. Anyway, so now we have this, right? So what about if I would like to make an adder adding two numbers, and I would like to see what will be the final output, right? So if I have a BCD number added to another BCD number, right? And we know the full adder, right? Philosophy we used before, and we especially using the rebel carry adder. So end of the day, I'm gonna have a unit. It's called 4-bit binary adder. You guys agree? So they're gonna be 4-bit. That guy is gonna be 4-bit, and we're gonna have a carry in, and we're gonna have here a carry out, and then we're gonna have output of this process, and this output is called Z, and it's actually 4-bit. But this is just a binary adder. This is not showing me how the process to be done to be 0 to 9, right? Because think about it, right? This is actually 0 to 9. This is 0 to 9, right? Some of the cases will be greater than 9 for Z. You guys agree?
Yeah.
So in that case, we need to have something here that will allow me to add 6 sometimes or to add nothing some other times. That makes sense? So that means we need to have a checker. So people say, what about if I just make a 4-bit binary adder? Okay, and that will be my official output, and I will call it S, and this is 4-bit. But then people will come and say, what exactly you're trying to add here, right? So I can tell you the second operand here, it can be 0 or 6, right? So we need a kind of a checker allowing me to get to either that it's gonna be 0 or 6. For instance, if Z is 0 to 9, I'm gonna add 0, so the S will be 0 to 9. For instance, if I'm above what's called above 9, then I have to activate this to be what? To be 6, and then I will move forward to add it, and then I will get out. That makes sense? Everybody agrees with me?
Yeah.
So if I look to 6 in general, I will find it 0, 1, 1, 0. Do you guys agree? So in that case, if I compare it with 4, 0 like that, I will find out that the 2-digit in the middle, the one, it can be flipped to 0 and 1, and then the whole entire system will be fantastic, right? So I can look more into the second adder here, and I can break it into like this: 0, 0, and then something here, right? And the Z and S, and they're gonna be 4-bit adder. What is this something here? They're gonna be a combinational circuit. It will fill the value of Z, and from there it will decide whether that that can be 1 or 0. Do you guys agree with me?
Yes.
So it's whatever I'm talking about now, it's clear to everybody or not? That's my question. Is it clear to everybody or not clear to everybody?
Can you repeat it again, Professor?
Yes, sir. So think about it, right? Z, it has to be added to something, right? And if Z is 0 to 9, I don't need to add anything to it. Do you agree? Because the output is 0 to 9. So in that case, I need my circuit to be smart enough to make this wire 0. Then those two will be 0, so that means I'm adding Z to 0. That makes sense?
Yeah, okay.
Then when Z jump more than 9, I need this smart circuit to recognize the output of it. It will be 1. So that 1 will be 1 here and 1 here. So that means Z in this case will be added to what? 6.
So you need a comparator?
Whatever we're gonna see now, right? So see, you know, we are trying to find a solution now. That's really, really nice, right? So we are building a kind of a simplified comparator. Because, you know, you take it like this, right? I need something, it takes Z, and it bring me out here whether they're gonna be 0 or, you know, be more specific. You just like, I need one output. Either gonna be 0 or 1, right? And then I take this output and I will connect it like this, right? And then I have here officially 0 and have here officially 0. So in this total will be what? It can be holding 0 or can be holding 6. You guys agree? And here is a combinational circuit. And here is Z.
Can
Right?
you give me an example of it?
Yeah, we're gonna go through it like now smoothly. So, you know, in general, you understand what I'm saying? If you look at it very carefully, right? I have here a binary adder. It's just a normal binary adder. Do you agree? This binary adder is adding 2 BCD numbers. Do you also agree?
Yes.
So what is the maximum BCD number here it can be?
9.
9. What is the maximum can be here? 9, right? So that means 9 plus 9 is what?
18.
18. And here is, you know, C is can be 1, right? Who knows? It's maybe coming from another partition, right? So that means, you know, what is the maximum of this Z can be? 19. Right? So that means Z is holding value from 0 to 19. Do you agree?
Yes.
So if you look to 0 to 19, 0 to 9, you know, the circuit, it has to give me officially the output as 0 to 9.
Yes.
But if I'm above 9, I need something which is adding 6 to the value so I can return it back to 0 to 9. So one of the way to do it is to actually to extend Z and you put it in another binary adder, right? Then you will need here a kind of nice circuit, and this nice circuit will be converting to 6 or 0. It depends on my what output. That makes sense?
So if it's 11, will it go back to 1?
If it's 11, you have to add 6 to it, right?
Oh, okay. So it'll go to 7 then.
Yes. Maybe I can draw it in a nice way. So look at this. Here, you know, I need something like this, right? Binary adder, right? And that's 4-bit. This is what? BCD1 or BCDA, right? This is what? BCDB. Do you agree? This is carry in. This is the carry out of this stage, right? Now my output is called what? Z. Sounds good? This Z, it has to go somewhere into another BCD also. So gonna be 4-bit binary adder, right? And then, you know, the input here, it's gonna be here a combinational circuit, taking this guy into the consideration like this and bringing me what? The output, right? And then, you know, that will go into what? Final result of the Kaby look ahead. The BCD. So S will never go above 9. It will be 0 to 9. Do you agree? What is this circuit is doing? Think about it like this, right? Here I have to add 0 or 6, right? Can we write it down? So gonna be here 0, 1, 1, 0 or 0, 0, 0, 0, right? So that means 0 here common, 0 here common, right? Which one is different? This 2 and this 2, right?
Yes.
So I can build a nice circuit like this, right? Look, I'm taking Z here, look, and then, you know, my output will be like this. 1 bit, and then, you know, here's 0, and here's 0, right? So this 1 bit, it can be 0, then this will be zeros. Then, you know, this 4 will be representing 0. If this is 1, that will be here 1, and this is 1. So they're gonna be representing what? 6. Now we understand what I'm saying?
Yes.
Is it clear to everybody?
Yes.
Okay. Now we need to make a truth table for what I'm saying. That will help us to identify what is inside this block. right? Something inside the block. So since, you know, this block is taking Z, and I know Z, it can be 0 to 19. So that means my inputs in the truth table will be 0 to 19. Do you agree?
Yes.
Exactly. So I'm going to go now build a table like this. And this table will be the following. What this table will be, it will be my final output as a BCD sum. And my input is the binary sum, which is this one, of Z, right? So I have what? I have Z1, Z2, Z4, Z8. Okay. And then I also have what? The carry out here. So that's called K. Okay. So far, so good. Now, my output, it's gonna be those S, right? So gonna be S, S1, S2, S4, S8, and perhaps I will have also official carry out from the 6 plus whatever Z, right? Because, you know, let's say I'm adding 6 plus 10. So what's the output? 16, right? 16 is, if you take the 4-bit, it will be 0, and there's a carry out coming out. So this, I'm gonna call it C. Okay. Now we said this table will be covering what? Cases from 0 to 19, right? So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Somebody will tell me why 20, because it's 0 to 19, right? So now I'm gonna start writing. So 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Then, you know, here 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1. And then, you know, I go here 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And then here is 8. See, I write here 8, that means 8, 0, 8, 1. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. I don't have anything to continue, so I'll just keep it as it is. And then, you know, here 16s, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then, you know, 1, 2, 3, 4. I can continue 16, but I don't need it anymore, right? So everybody know what I already have done in the Z side, right? Do you agree?
Yes.
And you know why I call them Z1, Z2, right? Because see here I Z1, right? So basically 0, 1. Z2, 2 zeros and 2 ones. You know, Z4, 4 zeros and 4 ones. You know what I mean? Because it's 2 power 0, 2 power 1, 2 power 2, 2 power 3, and so on. Now, when my output is 0, basically when my input is 0, it's within the 0 to 9, right? Everybody agree?
Yes.
So pretty much I know that my output is 0, 0, 0, 0. So that means I don't need to add 6, right? So that's actually the case for even 1. And this is actually the case for 2. And this is actually the case for what? 3 and 4 and 5 and 6 and 7 and 8 and 9, and that's it. So those are the section that, you know, my output, it doesn't need, my output from the first stage doesn't need to be added to 6. Do you agree? Now, 10 then it has to be added to what? To add 6 to 10 back to 0 to 9. Do you agree? Hello?
Yes.
In that case, 10 plus 6 is what? 16. Right? 10 plus 6 is 16. So here's 16. Can you see it now? 17. 18. 19. 20. 21. 22. 23. And 24. And 25. It makes sense to everybody? Hello? Hello? Can you guys hear me?
Yeah, sorry.
So now it makes sense to everybody. So if you look to the S, you will find all the number in S. Just do it like this, right? You will find all the number in S now is what? Between 0 to 9, right?
Yes.
Now we need to build a circuit, right? How are we going to build a circuit? It's very straightforward, right? Why is straightforward? Because now when is the outputs will be causing me to flip. So the output will be causing me to flip here, right? Before that, it was 0. So before that, I need the output to be of the combinational circuit here to be 0, right? But when it will start to be 1, when I see this with those, right? Do you guys agree? So I need an AND gate to take Z8 and Z2. That's AND gate. It should give me the output to be what? To be 1. So I can do it like this. Right? Is that the case? No, still I have more cases. So also the cases of the here, right? Those are the only unique section also can give me the output to be 1. So in that case, it will be Z8 and Z4, right? Z8 and Z4. What else? Also when K is 1. So here is also when K is 1. That will be what? That will be called call it P. So then, you know, I can pretty much build my circuit to look like that. The second 4-bit binary is taken here Z and is taken P like this and taking this 0 and this 0. And that will be S. Now, does it make any sense to everybody or it's not clear?
Can you go back and explain the truth table one more time?
Sure. So, you know, let's see, right? Let's see, pick up one of the inputs and tell me, you know, test it. And let's see whether it will work or not. Just testing it, right? So let's pick up this case. Let me just use a different color here. So let's use this case, right? And see what will be the circuit coming out of here, right? So here, for instance, Z1 is equal what? 0, right? Do I have any Z1 here? I don't care that much. I care about Z2. Z2 is equal 1, right? Z2 is equal 1. Z4 and 8 equal 0. Z4, 0 is equal. And then, you know, k is equal 0. Right? So since Z8 is equal 0, so I'm pretty much know that this output and this output is 0. Do you guys agree? Then k is equal 0, so that means the OR gate output will be what? 0. So then that 0 will go here and here, so that's 0, 0, 0, 0, that's actually equal 0. So the value in that case will be added to 0, and that will be S. That makes sense?
Yeah, but can you explain one more time to me how you got Z2, Z8, and Z4?
Oh yeah. I'm trying to build, do you remember when I told you that, the combinational circuit, it will take Z1 and Z2 and Z4 and Z8 like this, and it will
Yes.
produce to me like a wire like that, and that wire will go like this. Do you remember? And then that will go here to be 0 and 0, and that will be the second operand added with Z. Remember that? And that will be S. Do you remember? Have you seen this
Yes.
before? Yes, and this is
Yes.
actually the second 4-bit adder. Right? Now, I need to build this combinational circuit, right? So this combinational circuit is this part. How? Right? If I start looking here, right? Between 0 to 9, this case is, I'm fine, right? I need to get the output of the combinational circuit to be 1, right?
Oh, so you look past you look past the 0 to 9 and you only look at the bottom. Okay.
Right? Because I know that from 0 to 9 here, this combinational to be 0 here, which is gonna distribute it to be 0, 0. So that means 0 will be added to zeros, right? Now I'm looking to the second half of the table, this one, right? I'm starting to find similarities for a circuit will cause me 1, right? So for instance, if the Z4 is actually Z8, right? If Z8 is equal 1, right? Can you see this? Z8 is equal 1. And I found that, Z2 is equal 1, right? So I'm talking about this statement, right?
Yes.
In this case, really, I need 6, right? That would be 6. Do you agree?
Mm-hmm.
So in that case, I nominate this part by this AND gate. So that's actually Z2 ended with the Z8. Then, those the only 2 cases in the table? No, there is also some cases in the table, which is actually those guys, right? One second. Those guys, right? Can you see them? So those guys, I'm trying to find what is the common thing between of them. So I found out that, Z4 and Z8, if they exist at the same time, that will be actually covering this area, right? So that's why I put Z8 and Z4 together with this AND gate, right? Then what about the rest of the table? The rest of the table, this area, right? So the rest of the table in this area, I just found, K is the only one here, and it's a unique. So I took it as a K here. Then I OR all of them together. So for instance, if this exists, that will be covered as 2. If this exists, that will be covered as 4. If this exists, that will be covered this area. So that means I cover the whole section that it will cause this pieces to initiate 1, which will be propagating to be 6. That makes sense?
Yeah. Okay. So you're just trying to cover the entire table from
Exactly.
from the bottom half. Okay.
Exactly. So let's try some number. Pick up a number. Which state you like? Should we go in the state? So the state, right? Now I'm putting everything 0 except K is 1, right? So here's 0, here is 0, here is 0, and here is 1. Anything ORed with 1, it will be 1, right? So it did a good job because this 1 will go here to be 1 here and 1 here. So it's going to be 0, 1, 1, 0. So this circuit is presenting what? 6. That makes sense?
Yes.
Any question? Anything, it's not clear? Please, don't hesitate. I'm here for helping. So if it's not clear, I can repeat. There's no problem. You can just tell me exactly where should I repeat. I will repeat.
Where does that
That's it.
carry out go to on the last binary?
Which one? This guy?
No, on the 4-bit adder, yeah, your carryout, where does it go out to?
To C,
Yeah, because
that will be our official carry out. That's a very good question, actually. Yes, that will be the official carry out. Yes, you're right.
okay.
And by the way, have you noticed something, Andrew? That carry out C is one in this area, which is correct. You know why? Because this is a specific area in the table needs 6, right? Need to be added to 6, right?
Yes.
So that's actually going to be our official even carry out. You're right. So that also can be taken away like this, carry out of the circuit. Right?
Correct.
Professor,
Okay.
could you have also found that relationship through doing a K-map as well? I know you just examined the table and you're able to come up with. the
Yeah, I mean, you can make a K-map. That's perfectly fine. I mean,
Okay.
how many K-map you can have? 1, 2, 3. But don't forget, this is 5 variables.
Okay.
Oh, a 5.
5 variable K-map.
Oh, wow.
That. Oh.
Got it.
By the way, there is no problem. We can make 5 variables K-map. You know how? I will show you a trick. Let's build the majority encoder. This is just an example to make it very easy, right? So majority encoder, 4 inputs, okay, using 2, 3 variable K-map. Did you hear what I said? So, majority encoder, it was a 4 variables, right? Like an X, Y, Z, W, and here is P, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm going to show you now how can you use smaller variable, a small number of variables with combinational elements like multiplexers. So for instance, here I have 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? Just do it fast. They're gonna be here 0, 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 gonna be here 1, gonna be here 0, gonna be here 0, gonna be here 0, gonna be here 1, gonna be here 0, gonna be here 1, gonna be here 1, and gonna be here 1. Everybody agrees with me? Now, I'm asking you to do it with what? With 3 variables K-map, not 4 variables K-map. So it is really easy. You know why? Because, if you look to this table, you will find out if I take those 3 together, right? You will find in this particular area, look at this, the table is identical from here. You guys agree?
Yes.
Yes.
The only thing when X is actually 0 or 1, right? So what I can end up doing, I can have here P1, P2, and then I will do like this multiplexer, right? When it's 0, when it's 1, here is P1, here is P2, and the selector in this case will be what? X. And that will be P. What do you think?
That's pretty cool.
Yes.
Okay.
So in that case, I can make a K-map number 1 like this. 1, 2, 3. And then, I can call it here what? YZW, right? YZW. 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. 0, 1, 3, 2, 4, 5, 7, and 6, right? So in that case, I'm covering here. So I will find out P1 is actually YZW, right? So which is 7. So I can come and say P1 is equivalent to X, Y, X, Z, W, right? Then I can make another key map that will be the more work. So it's going to be 1, 2, 3, and then I will say also Y, Z, W 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, and 0, 1, 3, 2, 4, 5, 7, and 6. Here now I will start covering. That was 0. So in 3 is 1. 3 is 1. And 4, 5, 4, 5, no, 5, 6, 7 is 1. 5, 6, 7 is 1. So pretty much I can come and say P2 is actually 3 groups, right? So this is a group, this is a group, this is a group. So pretty much it's exactly as the carry out of the adder, if you remember, right? So that's actually X, Y, X, W, and Z, W. Then if I would like to build my own circuit, in this case, I can come and make it like this, multiplex 0, 1, and P1, it was XYZ, right? So I can just make here an AND gate X, Y, and not XY, I'm sorry, Y, Z, W. While this one, it will be this equation, right? And here is P, and here is X, and I finish it. So if you want to do the same similar things with the big table like this one, you can also do it like a 2K map, right? And you can consider the rest of the table, which is I didn't cover from 19, right? Either that you will make it as a don't care, or you would like to make it as what's called don't care or Z impedance, so you can put them 0. It depends on how you would like to optimize. That makes sense to everybody?
Yes.
Professor, isn't P2 ZY and YW
Huh?
on the scroll down? You have X on P2. It should be
This is Y. Why?
no on P2. You have X's in there?
There's no X. You're right.
No, in the formula. Yeah.
WZ, 1 second, I'll fix it to you.
It'd be Z
Y,
yeah.
W.
and the X should be Z, the other X. Yeah, there you go.
Yes. Yeah, but you understand the concept. That's all I do. Okay. $5.
Oh,
Yes.
okay. So the top table can be made into a 4-bar K-map, right?
Which one?
The top one, the one we were working on.
This one?
Oh,
You mean the BCD?
Yeah, that one.
It's going to BCD. Okay. What?
Yeah, that one.
Limit.
This one can.
This one is a five variables. So that means you have to cover city too, right?
So I can't split it into P1 and P2.
You can do whatever you want. You can even split it. You can split it even 4 K maps with 4X multiplexers.
Okay.
That makes sense? I would show you
Yeah.
actually. Look. You know, did you see this? Right? Those guys are the same like those guys, right? As the same as those guys. As the same as those guys. As the same as those guys, right? So I can make these 2 little guys selector for multiplexers, and then I will have 4 easy peasies AND gate or XOR gate, whatever, you know? You understand what I'm saying?
Yes, sir.
Yes.
Super. Any question? Any concern? Any answer? Anything? In this particular case, I can say that we finished the most important part of the, we did the comparator, right?
Yes.
Yeah, so in front of me, the priority encoder, and you know how to build encoder for the 7-segment display, right? I know that you took in the 2300 lab, you already have the 7-segment decoders and all these things, right?
Yes.
But you know, what about if I like to build it? That's not really hard, right? So how? The 7-seg is like this, right? A, B, C, D, E, F, G, and if you like to have the dot, let's call it N, maybe, right? So if I like to write here 1, what should I do?
Wait, what do you mean? Wait, sorry. What?
If I want to make this 7 segment presenting 1,
Is it a cathode or anode?
it doesn't matter.
Oh, just turn on BC.
Yeah, so gonna be, let's make it, it's gonna be B and C, right? So that means, if I
Oh,
make
you
it,
wanted the physical number 1. Oh, I'm an idiot.
yes, exactly, presenting it. It's like representing on the 7 seg. So you can actually build a table, and this table will be acting the decoder system, right? So you can just write here, for instance, it's a 4-bit switch. It will be controlling this guy, right? So I can actually call it like B3, B2, B1, B0. And then how many outputs I have, and I have A and B and C, D. So gonna be A. Why is this guys like this? A, B, C, D, E, F, G, and N. So I have how many outputs? 1, 2, 3, 4, 5, 6, 7, 8. That will be connected to your 7 segment, and it's actually turning on, right?
Yes.
Then this table will be how many states?
16.
16, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16, right? So here is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. 0, 1, then 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, then 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 7, 8, right? Now, I want to present physical 0 on the 7 segment display. So that means I would like it to be like this.
Just have to turn on G.
Right? So that means, everything is on except G, right? So gonna be here 1, 1, 1, 1, 1, 1, 0, 0. And you will continue filling. And as you ask, is it a common anode or cathode? So it depends, right? Let's say they're gonna be common cathode, right? So that means the anode, it has to, every single element of this is actually anode, right? So I have to connect it to 1 to turn it on. If it's actually common anode, then every single one, it will be cathode. So then I have to flip this number to be zeros, and then G and N will be 1. That makes sense?
Yes.
Then you will fill up the table. Like for instance, here C, I would like it to write C, for instance, right? So writing C gonna be like this. Right? So that means B and C is not exist. And C, B and C is gonna be 1, 0, 0, and then 1, 1, 1. Oh, B and C and G also will not be exist. 0, 0. Right? I wanted to write F. So F is like this. So basically B and C and D will not be happening. B and C. So B and C and what was the other one? D, right? D, and then 1, 1, 1, 0. And you continue.
Is this hex? Are you doing hex?
Huh?
Are you doing hexadecimal?
I mean, if you want, yeah, why not? Actually, you have to do hexadecimal. You know why? Because I cannot write 15. Because if I want to write 15, I need to have 2 7-segment display.
Yes. Okay.
Make sense? Then you can also play with the system. You have to be tricky, right? So for instance, A, you can write it like this. If it's uppercase or lowercase, right? So if you wanted to write also like an uppercase, it's gonna be like this, right? So it's gonna be like this. Then the rest of those guys will be not happening. And you continue. So everything's clear so far?
Yes.
Yes.
Okay. So far, this course is the easy peasy lemon squeezy, right?
Yes.
Okay. So I want to thank you guys for the time and the effort you are doing due to the pandemic and during the pandemic. And don't hesitate to contact me. I will be more than happy to assist you. So next time we're going to be talking about the priority encoder, which is highly used as an interrupt unit for those people who really like programming. So in a microcontroller, for instance, there is, as you know, there is limitation of units of computation units on the chip. So they have a priority encoder which will organize the relation between the computation versus the peripheral you are trying to communicate with. We will talk about this more on this coming Monday, and then we will move to the beginning of the sequential circuit. If there is no questions, if there is no concern, if there is no answer, I'm more than happy to end up this class for today. And I wish you a wonderful weekend. God bless you and stay safe. I'll see you Monday.
What circuit was your FPGA?
Filled programmable gate array. So there is something, it's called FPGA. Filled programmable gate array. Then this is more into digital, but then the people from Georgia Tech, they built something else and they call it FPAA, which is the field programmable analog array. And each one it has its own pros and cons and application. So for instance, FPGA now can be very expensive. So for instance, here Xilinx give me one for like a $45,000. But then you have another one here, which is like $300, $200. There's another one I have here somewhere in the fifth dimension. It's basically like $150 or something, like this. So it depends, Okay, but the concept is the same. You're gonna use HDL, hardware description language. So it's called HDL, hardware description language. And those are three. Verilog, 3300. System, Verilog, 4305. And VHDL, and this is 4304. Those are the classes, the courses we are teaching here at Capoli. And then there is another branch of science. It's called HLS, which is high-level synthesis. You write C, and then the compiler will turn it to HDL, and then you will map it on FPGA. There is a big branch of computation science in this. We can talk about this later if you guys are interested. Any question?
No, that's it. Thank you so much.
Super. So God bless and stay safe, please, okay? And have a wonderful weekend. I'll see you on Monday.
Thank you, Professor.
You too.
Thank you, guys.
Have
Thank you.
a good
Bye. Thank you.